Welcome to DigitalWERX TV. I'm Steve Johnson, and I'm with Ron Porter. I have to read Ron's job title. Vice President for Curriculum for DigitalWERX. So you're part of all this.
Yes.
And today, we're going to talk about systems thinking.
Right.
Which everybody's going to, what, systems thinking? I don't think I'm going to enjoy this. But you are, because you do systems thinking every day. And for instance, for us this morning, this is our system. This table, the computer, the microphones, the headsets, the cameras. This is all part of the system to make this podcast work. And we think of things like this without knowing we're doing systems thinking. It's part of our lives, but it can be done much better and much deeper than most of us do it. And that's what you're going to explain.
I started to say, you've already got systems thinking down. Don't know how much I have to explain to you. But you're right. This is a system, and thinking about a system is important. And you can do it in the way you normally do it every day, which is perfectly fine in most cases. But you need to do it in a very disciplined way for certain cases.
Okay. So what's a simple system that you, I kind of gave one for this, but what's another system that would be an example of a system and thinking about it as a system? What's an example?
So let's get simple here. Here's one.
Okay.
A pencil. It doesn't seem like a very complex system, and it doesn't seem like a system at all until you start recognizing what it is. And what it is a series of interrelated parts that perform a purpose. Okay. And so, yeah, a pencil performs a purpose, right? So you can write things down and erase things. And it's got multiple parts, which is kind of surprising. It has the wood, and the wood's job actually is to protect you and hold together this little part that you write with, which is graphite. And then at the end, there's this little metal ferrule that holds on the eraser. And of course, there's paint over the top of it. So This is a whole series of parts that are interrelated that form the purpose of a pencil. So there's your one right there.
And one simple statement is you have to have more than one part to have a system.
That's correct.
But every system is made up of parts.
That's right. That's right. And
I feel all brilliant for saying that.
Yeah, well, I mean, it's pretty simple. Now, the more complex you get, the more parts you have, the more you have to group them into different groups. And so you'll have a system, and then you may have a subsystem, which is in itself a system, but with those other subsystems makes a greater system. So a car is a good example of that. Right. So you have a engine subsystem, which if you build engines, that's your system. But to the car manufacturer, that's a subsystem, right? So that's how the disciplined approach of putting together a system. So system, subsystem, sometimes there are components down below, which is a bunch of parts that form an active thing, but that active thing doesn't really have its own function other than to support another thing, and then parts down at the bottom. And frankly, even system engineers use parts and components interchangeably. So.
Okay, and this may be a good point just to say that a systems engineer, say a systems engineer for a new sports car, there's somebody who's in charge of the whole.
I want that.
So somebody's in charge of the whole thing,
right?
But probably other systems engineers are involved. But he would think of all the subsystems: the brakes, the windshield wiper assembly, the light, the electronics, the things that make the car work. A systems engineer would think of those, but all those subsystems go together to make the big system.
Right, and you bring up something because I know somebody's saying, well, I helped put the car together and we didn't have a system engineer. In reality, system engineers exist in a variety of forms. If you watch Star Trek, Scotty is a chief engineer. Yeah. Well, he's really a system engineer.
Yeah, because he knows where the lithium crystals are and what they do.
Right.
And all those good things.
Exactly. but somebody who works on a car for a living and knows everything about that is really a system engineer of that particular system,
Okay.
right? But yeah, there's always for a system somebody who knows in detail how all the interrelationships between the parts and how they affect each other.
Okay, now we've kind of gotten past systems thinking a little bit here.
Yeah,
We've
yeah,
gone on to the big picture, but
You'll back up?
the smaller picture though is that systems thinking is something that if you want to be a systems engineering technology modeler, you have to learn systems thinking.
Oh, absolutely.
But for the average person, I mean, after we start talking about it, I realize how often I do it or attempt to systems think.
Right, right.
So it's a great skill to have, but for somebody who wants to be a modeler and build systems and things like that, it's crucial. You can't be a systems engineering technology modeler if you can't systems think.
Yeah, that's absolutely true. And like you said, most people systems think, but it's the disciplined approach to system thinking that's required to do a system engineering or a system modeling job.
Okay, we all rankle at the word disciplined.
Yeah.
But
yeah.
So when you say that, what do you mean?
Okay, so you started it off a minute ago. You were talking about a system. We got to subsystems, we got to components, and we got to parts. That's an easy thing to talk about, but that is a disciplined way to take a system that's big and tear it down into individual units and use a language to do it. So there's a language that goes with the discipline of system engineering. Systems thinking is something you do, but not something that you spend a lot of time thinking about doing. You know, we think all the time. We probably think more than anything else we do, but we don't think about thinking very much. But
Maybe we should.
yeah, right. So systems thinking is bigger than just, for example, if you look at a car, let's say you're doing systems thinking about a car. So the system, and we call that here's another word in the vocabulary, the system of interest. So here's the system. You draw a boundary around it to make sure you're clear on what the system of interest is. You and I were talking about refrigerators in this regard. So if you had your refrigerator at home, look at it, and then using the skin of the refrigerator, that's the boundary. Everything inside that boundary is refrigerator. Everything outside is environment. Okay. So you first make a boundary, and then you look at all the interrelationship of parts inside of it, so forth and so on. But you also have to think about its relationship to other systems.
Okay.
So like a car, of course it lives in our environment, right? So if you wanted a car to drag race in the Sahara Desert versus one you wanted to take to Alaska, the environment makes a difference.
Yeah.
Right. So looking at and knowing the vocabulary of how you do all that classification and discussion is very important. It's a disciplined activity. Okay, Sorry about using the word discipline.
No, I know. Well, it's okay. I need more discipline. Go back to the refrigerator. Okay, you got a water line if yours has an ice maker, and if it doesn't have an ice maker, you bought the wrong refrigerator.
Right.
And you need to go back. And it also has a power cord. Without the power cord, it doesn't work. So
right.
What do you call those things that aren't part of the system? Well, maybe you could probably argue the power cord is.
It depends on how you draw the boundary.
Yeah. But if you're doing the skin of the refrigerator, the power cord would be an extra, and the water line. But so, what do you call those things? The things that aren't of the system, but make the system that are necessary to the system.
Right. Well, if they directly touch the system in either a functional way, help it work, or an actual physical way, you call those directly related systems. Okay, they're related because they're related. They have a relationship with the system. And you call those spots that touch, you call those interfaces, right? Sometimes we say, I'm going to go, Steve, you and I are interfacing right now. Well, we are, and where we touch is the communication we have going, the information that flows from me to you and you to me.
So systems thinking includes considering the interfaces with things outside the system.
Yeah, that's absolutely
I'm
right.
feeling smarter by the
Oh,
second.
you're doing great.
Okay.
Too.
Okay. Now I want to ask you. You've got some really cool graphics.
Sure.
That you can illustrate some of the things about systems thinking that people need to consider.
Right.
I'm sure not everybody, but some people are saying, well, I get the systems thinking thing. I mean, it's not complicated. You think about the fridge, that, but there are pitfalls. There are things
Yes.
you can miss when
Right.
you do systems thinking.
Right.
So let's talk about the elephant.
Okay. Oh, yeah, the elephant. Right. So sometimes when you're looking at what you think a system is, you need to look at the related systems that you discussed, or at least where is the boundary is unbelievably important. And you use this in your everyday life.
I get the feeling that the boundary is one of the places where people make a mistake.
Oh, it is, absolutely.
So they think they've outlined their system, but their outline's too big or too small.
Right. Well, let's talk about the power cord thing.
Okay.
So I'm going to go buy a refrigerator. What did I mean by refrigerator? What do I assume I mean by refrigerator? Well, if I were just you and I going out to buy a refrigerator for our house, we would assume the power cord is included and it can plug into the outlet in the wall. If we happen to be professional cooks and we're buying a refrigerator, they usually don't have a power cord that plugs in the wall. Usually the wall cord comes to the refrigerator and it's attached using screws. So one of the things you have to check is, I'm buying a refrigerator, does it come with a power cord? Now there's a case of making sure your boundary is right. Yeah, it seems like a simple one because most of them do nowadays, but used to be they didn't actually.
You're actually making me think, and anybody who has bought a dryer will understand this.
Right.
Because the cord is not attached to a dryer, because for some unknown reason, I'm not sure anybody can explain this, the wall receptacles for the plugs are there's two different main kind. Right. So you have to get a cord for your dryer that fits that receptacle.
And the vent that comes out the back.
So basically a dryer is useless without make sure you attach the right power cord in the vent.
Right.
But so that seemed like that's a system that has a definite boundary, and you have to have the things that reach out and touch the dryer to make it work.
Now, for us in our normal lives, that's a pretty simple one.
Yeah.
When you get into very complex systems, those boundaries become very difficult, and you have to really discuss, especially if you're building a system while someone else builds a system to relate to it. And hey, I'm a NASA guy, so I have to say a rocket and a launch pad. You're going to use the launch pad to fuel the rocket. Well, when the rocket takes off, it's not going to take hopefully, it's not going to take the gas line with it. So it has to break somewhere. So that interface discussion is extremely important. But let's talk about the elephant for a second.
Okay.
Because it comes back to that.
Okay.
Okay, so it's a famous story. It goes around. You may have heard it. Pardon me if I already tell it again.
I don't think I've heard it.
Okay, well, if you took several people and you blindfolded them, and you said, I want you to go forward and touch whatever's in front of you, and from that touch, tell me what you're touching. So in this case, the people are going forward and only seeing part of an elephant. And so in this picture, you can see every person who went in and touched a certain place thought something different. The guy in the middle, suddenly there's this big wall in front of him. Okay, well, I may be looking at a wall. The person who touched the tusks on the elephant, I think it's a spear or some sort of weapon. And the person who touches the trunk, I don't know what this is. It feels like a snake, but it's a really big fat snake, So each person draws a conclusion because they're not allowed to see the entire boundary of the system, only a piece of it, right? So if they backed up and took their blindfold off, they would go, oh yeah, okay, I get it now. I understand the whole system that's involved here. But what you take away from this is you really need to look at a system and understand it in its entirety to really understand what you're talking about.
Okay, so And I can see where somebody who's learning to be a modeler, systems engineering technology modeler, needs to remember that the part they're working on or the system they're working on is part of something else.
Right.
And they have to be thinking about how it fits in with everything else, so they have to understand the overall system. For just the average person, and once again, and we systems think, but this is probably one of the things we do wrong. Hey, if I hook this up, I'll fix my heater, my water heater. Oh, but if I don't seal that, my water heater is going to leak, and
Right.
I'm just an example that I've done where I didn't think about the whole thing, and it doesn't work.
It's really difficult when you're looking at large, complex things.
Yeah.
Like if you were to look at investing in the stock market, buy low, sell high. Yeah, that's a good tip. But how do you figure out how to buy low and sell high? If you're really invested in doing that kind of thing, you have to learn beyond just the stock market information. You have to learn the companies, how they work, all that sort of thing. I don't know many people who invest in the stock market, but you would have to look at the whole system of systems and how that works.
Is it hard to teach this skill?
No.
I mean the fact that there's a lot to it.
Right.
But is it, there are students, and this is one of the things they've got to learn to do to move on. If you want to be an engineer, you have to learn to systems think.
Right.
Or you'll never make it.
Yeah. In fact, I always like to say that even the 4-year engineering school's primary job is to get you to think systems level. But it's really not that hard to think systems level. If you were to come through, for example, a system modeling class, and the first one we teach, by the way, is Introduction to System Engineering, which is how to systems think. Folks who are uncomfortable systems thinking don't really proceed.
Yeah.
People who kind of have the idea on what systems thinking are, they excel. And system thinking is trainable. Once you have the feel for it, then you can train yourself to make it larger, expand it, and also make it more, disciplined.
No, you made me think of something. While you were talking about that, I think, and this to me is a good example. If you're, and the reason I have a friend in New York, and he was talking about going to the Metropolitan Museum of Modern Art. You can look at a huge painting, and you could fixate on one narrow area, but you really need to look at the whole painting for the real impact.
Right.
And it could be a large canvas. You're not looking at one part of it. You're taking in the whole thing. And it doesn't seem like that would be a talent or an acquired skill, but it kind of is. Where you can see the big picture, looking at a big painting. But seeing the big picture is sometimes hard because your mind doesn't want to work that way.
Right. Well, so have you ever done an all black crossword puzzle? There's no picture on.
No, I haven't. I saw the picture you have of that.
Jigsaw puzzle.
Yeah, I know people that do stuff like that.
Yeah. So that's a particular skill of, it's an analytical thinking.
Yeah.
Does this piece fit this piece, so forth and so on. Personally, when I do a jigsaw puzzle, I put the picture in front of me, or the box cover. And so essentially what I'm doing is systems thinking. I'm thinking the big picture and what my purpose is, what my goal is. And then I do the analytical, carefully putting the pieces together part. That's a really good example of systems thinking.
Okay, I know when we were looking at your graphics, you had one about that.
Yeah, I actually have one where, how many times have you been frustrated by, you got all the pieces, you got a pile of pieces that came in a box and you expect them all to be there, right?
Yeah, oh yeah.
Yeah. Well, they aren't. One's missing, right? So you can see it, I think, in this picture on the right, there's a missing piece of the puzzle. You didn't know that. If you were to look at all those puzzle pieces in detail, you would never know that. It's not till you get to the big picture that you see something's missing.
Okay.
And that's less frustrating than if you were doing an all black jigsaw puzzle and you put it together and they all fit, but they didn't really fit, and there's a space missing in the puzzle.
Okay.
Both of these are big picture issues that you can't solve by looking at the details of the pieces.
Okay, is that a skill that systems thinkers have to
Yes.
to learn? That's one of the learning things?
One of the learning things is to always keep an eye on the purpose and the big picture of what you're trying to do. I've got another one here for you. Don't miss the forest for the trees, right?
Yeah.
You can spend so much time looking at the detail that you forget the forest is what you're really after. You really want a forest. But if you just look at all the trees, okay, we'll take a tree out here, a tree out there, we'll get some good lumber out of it. Have we destroyed the forest, or can it recuperate?
Yeah.
That's a big picture systems thing.
And that would be, and there are people who think like that.
There are.
That think, okay, they're looking at a forest or a group of trees, and they want to thin it out, but they want to leave the essential character there.
Right.
And so knowing which part needs to go.
Right.
And so what do you call that? When you're looking at a system, but you're winnowing out the things that are unnecessary.
Well, so again, on the chart here on the right, if you think of it back to a jigsaw puzzle again.
Yeah.
Okay. You have all these pieces and you know where you're going, but the pieces are just a big jumble of colors. As you start putting them into the puzzle, in this particular case, a mountain emerges in the picture, right?
Yeah.
There's actually a term for that. It's called emergent behavior. So if you start putting trees, say you started planting trees,
Yeah.
and you planted a whole bunch of trees, after a while, it would become a forest, and a forest has emerging properties. It becomes a shelter for animals. It creates a large shaded area where plants that need shade can start growing, right? So there are emergent properties of a system that you create that appear as the system is actually formed. So let's go backward to your question. As you start removing trees, you have to determine at what point you have destroyed that system's ability to have that emergent property. Right, if you thin it out so much that the sun comes through and the floor is all sunny, now you're going to lose all those shaded plants, and you're going to start getting the brush that's like sun.
You have to think about what the system is and what it needs to remain the system.
That's right.
And I was thinking of another question.
Well, before you go to it,
yeah,
you hit another point there, maybe inadvertently, but you hit another point, which is when you systems think, you think about now and you think about the future. So now is back to the car. Now is this is what the car is going to look like. This is going to operate, how it's going to operate. How's it going to look and operate 5 years from now? How's it going to look and operate 10 years from now? Based on that, you say, if you're a company, you say, I think it's going to work great for 5 years, so I'm going to set the warranty at 4 years, 11 months, and 29 days, right? That's how they systems think. They systems think that. They don't just make up a number.
Okay, what do you call it when there will be a system? You know there will be a big system, but you have to visualize it when it is not yet anything. Is that a question that makes sense? Somebody has to be able to see. Now, granted, you could make a drawing, an illustration.
Right.
This is what we're looking for. This is what we think it'll look like at the end.
Right.
But
a lot of people referred that as the word you used, which is vision.
Okay.
Here's my vision of what I'm going for.
And you mentioned rockets before.
Right.
The space shuttle, for instance, was never supposed to look, at the beginning, it was supposed to look like something else.
Right.
And there were requirements, things that changed as it went, but the original visualized system did not end up being what the space shuttle was.
Right. It started off as all pieces flew back down.
Yeah.
You know, the big booster landed in an airport, right? And then the orbiter that went to space also came back and landed in an airport.
So they had a visualized system, and requirements caused it to change, which I would assume is something that happens in engineering and in and modeling all the time.
Right.
That I thought we were doing it this way, but found out that right there doesn't work, or it takes too long, or something. So the system itself is constantly there's flexibility there.
Right, and the terminology, and there's several ways depending on how you approach it to call that's a trade-off or a trade-off analysis.
Okay.
Or an analysis of alternatives. You reach a point and you realize what you had originally planned to do isn't going to kind of work that way. Maybe there's 3 different ways to go. You do an analysis of alternatives and pick the way you want to go.
In fact, that was something that in talking to students in modeling who were wanting to become systems engineering technology modelers, they talked about how cool it was that there were multiple ways to solve a problem,
right?
To get the job done.
Absolutely.
And so that's something, you think part of you wants to say, well, if it's flexible, how can it be engineering? But
well, actually, it turns out engineering is all about flexibility.
Yeah.
You are going to run into obstacles. A lot of times they're obstacles of cost, right? You're going to run into something that says, I can no longer go the path I was planning to go. I have to figure out a different way to do it. And that's why when you start something and you end it, they're related, but they're not necessarily the same. The vision is, or the realization is different than the vision.
Okay, so systems thinking rather, starts out so simple.
Yes.
The parts of the pencil. That's a system.
Right.
And your hand is not part of the system, but it makes the system work. Or it gives the system purpose.
And it's a related system.
It's a related system.
You're a related system to this pencil.
So I guess what I'm trying to get at is that the systems thinking on one hand is very simple, but as the systems get more complicated and your thinking becomes more in depth, it does become some pretty serious thinking. I mean, you really have to think about what you're thinking about.
That's absolutely right. So even the system that you're building is built by a system, if that makes sense. So the team that you put together to build something is a system in its own right. Its multiple parts are people, and its multiple parts include computers and pieces of paper and telephones and all that sort of stuff. So that's a system in its own right. When they did the Apollo program, going to the moon, 400,000 people worked on that program.
By the way, if we hear any extraneous sounds, and I'm hearing some, there's some people utilizing some systems that look suspiciously like drills outside this building.
Right.
So don't pay any attention to the guy behind the curtain.
Right. They're changing the system that we're currently sitting
in. Yeah.
Right. As long as they don't come through the boundary.
It's not bad. Nothing bad's happening.
Right. As long as they don't come through the boundary, we're okay.
Yeah. Okay, where were you?
Okay. Well, anyway, so the everything can be considered. Almost anything that has interrelated parts that form a purpose can be a system. Organizations are systems.
Yeah.
There are process systems. Amazon's delivery system. But I'll tell you what. Let's play a game. Name some things that say system. Like you have a stereo system, or can you think of any?
That's the kind of thing, as soon as you ask it, my mind just clean slate.
Right.
Game system.
Game system, like a video game system.
Yeah, like a video game system.
Right. That's a system. I mean, it is. If you think about it, you put the boundary around it. Yeah. It has interrelated parts to perform a purpose. That's a system. Absolutely. The digestive system of a person. That's a system.
And the body, of course, is full of systems.
That's right.
The digestive system, the nerve system, the nervous system. So you've
right.
Yeah,
if you were a doctor for the digestive system, you would refer to that as a system.
Yeah.
If you were a general practitioner, you would probably not say this. If you were an engineer, you would say it's the digestive subsystem. Okay.
Not the system. True. Yeah, the body is the system.
Right.
They have subsystems.
Right.
Okay, so I think is there any part of systems thinking that we haven't mentioned yet? And we mentioned everything from, outlining what your system is and understanding parts that come into the system. What did you call those? Like your hand with the pencil. Your hand is the.
It's a related system.
It's a related system.
Right.
But is there any part of systems thinking that you want to make sure you mention while we're talking about this?
Well, so one of the ways to train and hone your systems thinking is to think about systems. In generic, generic discussions about elephants and jigsaw puzzles are nice to get the point across.
Yeah.
But if you want to make it better, start looking at things around you and defining them as systems and putting boundaries around them. And when you start making decisions in your life, make them from a systems perspective. I'm going to buy a house. Okay, I'm going to build a boundary. Does that include the water meter or not? Is the gas part of it that's flowing in or not? Yeah, figure out what your boundary is. Then look at that same system, how it will look in 5 years or 10 years. Maybe you'll decide to have a brick house instead of a wooden house if you think about time. So start doing that kind of thing, and you'll find that eventually you'll do it automatically. And some people who buy houses already do it automatically.
Oh, yeah.
Yeah,
So that the colors of the walls do not fit the system they have in mind.
Exactly.
But that can be changed.
But yeah, you look at that and you say, what is the cost of making that system modification?
Okay.
Right?
So our life, basically, over the course of this conversation, our lives are made of systems thinking.
That's right.
We do it every day. And a modeler, somebody, an engineer, just has to do it more in depth with more detail and taking into account more variables.
Right, and do that in a structured approach that other people working on that system can understand.
Okay.
One of the things you really want to do if you're doing a systems thinking job is understand the language and be able to quickly talk to the people around you.
Okay.
So my very first NASA meeting I ever went to, I didn't understand 10% of what they said because they spoke in acronyms. It was very interesting.
I've listened to those conversations
before.
Yeah.
But applying a little mental discipline, I was pretty quickly, and I'm saying quickly, like within a month or two, spouting acronyms with the best of them. But that's just a language around that particular systems thinking field.
Oh, and all fields have their own jargon.
That's right.
That's just, but if you're systems thinking, you have to learn the jargon of whatever kind of system you're building.
That's exactly right. And system modelers, just like anybody else, have to learn the language of modeling as well as the language of the product or system they're working on. Right.
Cool. All right. And there's more to it. That's why they call it going to college.
That's right. That's exactly
All right, Ron. Thank you.
Sure. Happy to be here.
I feel smarter. Well, it's not hard to do that. Anyway, but thank you for joining us on DigitalWERX TV. And we're going to be talking about a lot more cool stuff just like this. And remember, it works.